Hello and welcome to a video on real zeros and their multiplicity. So this is about polynomial functions, and we're looking at the x-intercepts. Those are the real zeros. So that's just another name for x-intercepts is real zeros. Now just to give you some perspective, if you've seen my most recent video on end behavior, where we looked at what's happening on the outside of the function, what we're going to be looking at now is what's happening in this sort of mystery part of the function. So we're going to answer the question, what's happening between these end behavior patterns. Okay, so that's what we're going to focus on here. So first of all, like I just said, a real zero is an x-intercept. So we know that it's an x-intercept. If it's a real number, if it's an imaginary number, it can also be a zero, but it's not a real zero. X-intercept, okay. And a real zero is a number that makes one of the factors zero. And if one of the factors is zero, then that means that the value of the entire function is zero. So I'm just going to write that down. Okay, so what I wrote here is if f is a function and r is a real number for which f of r equals zero, then we call r a real zero of that function. In other words, if you plug in the number, that real number, and it makes the function zero, then that number is a zero. So if you have something like f of x equals, let's say, x plus 5 times x minus 4 times x plus 2. Okay, there's a function. Now if I plug in the number negative 5, that's going to make this function equal to 0. So therefore we call negative 5 a real zero. And that would be an x-intercept. Okay, because it's going to make y 0. That's what this is basically. This is what it's trying to say. So if you plug in that negative 5 here, you're going to get the value of the function is 0, and therefore we're going to call that negative 5 a real zero, making it an x-intercept. Okay, so the multiplicity of a zero, that's the degree of the factor. Now in this example that I showed you here, these are all assumed to be first degree factors. But if this were a second degree factor, then that would make the negative 5 have a multiplicity of 2. Okay, so we're going to write that down. Okay, so we have the multiplicity of a zero is the degree of a factor. The degree of a factor is called its multiplicity. For repeating factors like this one, for example, where the factor x plus 5 repeats twice, m is greater than 1. In this case, m is 2. In this case, m is 1. If I put a 3 here, then the factor x minus 4, which has the real zero of 4, has a multiplicity of 3. Okay, there are no negative or fractional multiplicities. That wouldn't make any sense, and so m is always greater than or equal to 1, and m multiplicity is an integer. Okay, so the rule about multiplicity is if a zero has even multiplicity, then it's going to end up being an intercept, an x-intercept that just barely touches the x-axis at exactly 1 point. While if it's has odd multiplicity, then that's going to be a real zero that crosses the x-axis as opposed to touching it and bouncing off of it. Okay, so let's just write that in here. Okay, so here we see a picture of a graph that has two x-intercepts with what must be even multiplicity, because you can see how it bounces off the x-axis. So if a zero has even multiplicity, the graph has an x-intercept that touches the x-axis but does not pass through it, and sometimes we say it bounces off of the x-axis. You can write that down too if you need a couple ways of saying it. Okay, and if it's odd, that means it crosses through it. Okay, so here's a polynomial function with 3 x-intercepts, and based on the graph we know that each one of these has an odd multiplicity. Could be just first degree, could be third degree or fifth degree, because it crosses through the x-axis instead of these even ones bouncing off of it. And of course, you know, a function can have a combination of even and odd. These are just examples that have just one or the other. Okay, so now we're going to look at a specific function. So we're going to look at this function right here, and we're going to follow the rules now, and we're going to just kind of identify what the factors are. Okay, so this function has 1, 2, 3, 4 factors. So there's 4 spaces here. So I'm just going to write in the 4 factors into the 4 spaces. Okay, so there's the 4 factors. Now each factor corresponds with a real zero. In this case, not always. It is possible to have a factor that has no zeros. If there's no way to make it 0. I'll show you an example like that in a minute. Let's just finish with this one. So here, the thing that would make this factor 0 would be 0. The number that would make this factor 0 would be 2, right? If x were equal to 2, that factor would be equal to 0. This one is a -3, and this one is a -5. Okay, so each one of them has an x-intercept. So this function has 4 x-intercepts, 1, 2, 3, 4. Now let's look at their multiplicity. This one is a multiplicity of 2, which is even. 4 is even, 3 is odd, and 1 is odd. So let's write those down. Okay, so there's all of the multiplicities, and I just wrote down whether they're even or odd. What really matters with the graph actually is not the number, it's just whether or not it's even or odd. If it's even, these two will behave the same way on the graph. They're both going to touch at exactly 1 point, and they're not going to cross through. These two, even though they're different multiplicities, they're both going to cross through the graph. And we'll see the graph in a minute, but let's first kind of describe it, see if we can predict what it's going to look like first. So even, of course, if it's even, that means it touches versus crossing it. So we'll just put touches here. Also touches, crosses, crosses. So let's write down what we know. So we have a function, and we know that there's an x-intercept at 0. We know that there's an x-intercept at 2. We'll just put a couple tick marks there. We know there's one at -3, and there's another one at -5. All right, those are all x-intercepts. Now we also know about them, but if I want to predict what this graph is going to look like, even just a little bit, I don't want to start out with the touching and bouncing part. I start out with the x-intercepts, and the next thing I like to look at is the end behavior. So let's kind of think of this function and see if we can collapse this. And this is not the topic of zeros. This is the other topic that's sort of looking at the outside now. So when we collapse this, you may remember that we get rid of all of the things that are being added and subtracted in the process of collapsing it. So what we are going to really look at with the end behavior is the power function that would be the first term. If we were to multiply this out, it would be a really painstaking process. We wouldn't want to do it. But if we did, our first term would be the degree of this polynomial, and it would be the power function that determines end behavior. So real quick, that would be -4x squared. There's nothing to collapse on that one, times x to the 4th, times x to the 3rd, times x. And if you multiply that out, you get -4x to the 2, 6, 9, 10. So this is -4x to the 10th. And because that's an even power function that's got a negative in front of it, we know that this is something that opens down. If this were just the power function and this were the whole graph, it would be something like this. Actually, it would be right there. It would be actually here. But the point is, it goes down as you go to the left and to the right. Well, we know that there's no other x-intercepts here. So this is the left and this is the right. And from there, it goes down. We know that. That's usually the next thing that I like to graph. Now let's see if we can apply these multiplicity rules and see what the function actually looks like a little bit. Okay, this one's a hard one to actually fully visualize, but we'll get at least an idea. It touches here, so it's not going to go through at the 0. Sorry, this one is 0. Let's start out with the -5. So there, it actually crosses there. So good, it goes through, so we can make it go through. All right, the next one is the 3. 3 is also going to be where it crosses. So it's going to go up. Eventually, it's going to come back down. We really don't know how high it's going to go, but we know it's going to come back down and cross the graph. All right, in this case, we already know the y-intercept. There's no point in searching for that point because we already see it there. And we know that at 0, it's going to touch. So it's going to go down. We don't know how far it's going to go down, but eventually it's going to come back up. But it's not going to cross through the x-axis. It's going to touch it. So sometimes think of that as bouncing off the x-axis. And then it's going to go to the 2, and it's going to bounce. So this is our 2. So it's going to go, eventually it's going to come back up, but it's going to bounce. So there's at least some idea of what this function looks like. Now, these numbers are actually pretty big when you look at it. So let's look at the function on decimals. Okay, so there's what the graph actually looks like. Now again, this is the function. Here's the 0 with a multiplicity of 2, so at 0, it's bouncing. And these numbers are already stretched quite a bit to be able to at least see the general shape of the function. It's bouncing there, it's touching just at that one point. Here at the x-intercept of 2, it's also even, so it's bouncing over here at 2. So it's bouncing off that. This would be very hard to see if you didn't already have that information. It looks like it's kind of, it could be anywhere in there between like -1.5 and 2.2 or something like that. Okay, at 3, or -3, it's odd, so at -3, it's crossing. So it looks like it's staying on the x-axis, but it's not. It's actually coming really close, and then right at -3 it crosses, and it goes below. And then at 5, -5, it also crosses. So what goes up actually comes back down, and you can see here it does have a top. Oops, it does have a top, but it's pretty high up there at like 200-something thousand, but it does cross again. And then forever, it goes down, and that's where over here and here, on the left and right, that's where it resembles that -4x to the 10th function. That's the leading term power function for this equation. Okay, so I drew over my graph, what it really looks like. And it's, you can see it's a little different, but the important things that we're looking here is the end behavior did match what we had over here, and that the intercepts matched, and it did cross and touch at the ones that we predicted. Okay, we're going to have the advantage of a calculator when we really do those. Okay, so now what I want to do is I want to be able to look at a graph and write an equation from the graph. Okay, so what I'm going to do is I'm going to name each of these R1, R2, R3, R4. I'm going to identify which ones are even or odd based on whether they touch or cross, and then I'm going to put them into a potential possible polynomial equation. Okay, so here's the connection between the zeros and the factors. If R1 is a 0, then x minus R1 would be a factor, because you subtract, you're going to get 0 from that. All right, and then this one we know since it crosses, we know that it's odd. So this is odd degree. Here it crosses, so it's odd, and so on. Okay, so we can see that there's only one of these that's even. There's only one place where the x-intercept bounces off of the x-axis, and the other are all odd. So now I'm just going to multiply these all together and call that my function. So f of x is, and I'm going to throw in an a here, and I'll tell you why in a minute, x minus just the product of each one of these 4. Okay, so there's my 4 factors, and because this one, R3, again, since it touches, it's even, I'm going to make that a square, make that a multiplicity of 2, and there's a possible function. Later, we're going to see how to find a. If we actually had numbers in the function, we'll do an example of that a little bit later. Okay, hope you found this helpful.